Right now, across the globe, billions of computers, phones, and servers are firing massive streams of data at each other every single second. If every one of those devices simply broadcasted its information to the entire network all at once, the sheer volume of traffic would cause the whole system to instantly freeze. So how exactly does a specific data packet navigate from a phone in your hand to a server in another country without getting lost in the noise or crashing the grid? The modern internet survives because of a highly disciplined two-part traffic control system: switching and routing. To see how this works, we have to start at the microscopic level. Imagine a single office building where multiple computers, printers, and servers share a closed local network. The physical traffic manager of this local setup is a device called a switch. It operates at what network engineers call OSI Layer 2, or the data link layer. To keep track of the devices in the room, the switch uses MAC addresses. A MAC address is a permanent, unique hardware identifier stamped directly onto a device's network interface card. This diagram shows exactly how a switch processes that local data. When a frame of data arrives, the switch checks the destination MAC address and forwards it down a single targeted line directly to the correct computer. The other connections stay completely silent. It is exactly like an internal mailroom sorting a letter and walking it straight to a specific desk inside the same building. By targeting deliveries, switching eliminates unnecessary local traffic. But it has a fatal limitation. A switch is completely blind to anything outside its own network. When data needs an external destination, it hits the strict boundary of that local switch. It needs a way to leave the building. That requires a router. Routers act as the gateway to the outside world, operating one step higher in the system at OSI Layer 3, also known as the network layer. At this level, hardware MAC addresses are ignored. Instead, routers rely on IP addresses to navigate the complex boundaries between entirely different independent networks. Here is a simplified look at a routing table. This is the router's internal map. It stores a list of destination IP networks, metrics for the best path, and the specific next hop address the data needs to take to move forward. Returning to our analogy, routing is the process of loading the building's internal mail onto a specialized truck that calculates the most efficient highways to travel between different cities. Switches organize the local room. Routers calculate the overarching global map. Together, they make inter-network communication possible. A network administrator can manually program a routing table using a method called static routing. But manually updating every path is incredibly slow and entirely unscalable for the modern internet. The solution is dynamic routing protocols. Routers are programmed to constantly speak to each other using specific algorithmic languages, continuously updating their maps in real time. This network map demonstrates one of these languages, the RIP protocol. RIP determines the best route by counting the sequential jumps, or hops, between nodes, stopping at a strict maximum limit of 15. To find even faster paths, other protocols are used. OSPF abandons simple hop counts to calculate the absolute shortest physical path. Meanwhile, Cisco's EIGRP protocol is optimized to calculate these routes with extremely fast convergence. At the highest tier is BGP, or Border Gateway Protocol. This is the massive overarching language used by internet service providers to handle routing across the entire global internet. Because these dynamic protocols allow routers to constantly share information, the internet can automatically heal itself, instantly rerouting data around severe congestion or sudden hardware failures. Let's track a single packet from start to finish. When a transmission leaves computer A, it hits the first switch, which reads the local MAC address and sorts it. The switch hands the data off to the local router. The router reads the destination IP address, checks its dynamic routing table, and identifies the fastest exit path. The data enters the open internet, bouncing between external routers that use BGP and OSPF to bypass traffic jams and push the data closer to its target. As you can see in this flowchart, the packet arrives at the destination network's router. That router strips away the IP layer and hands the data down to the final switch, which uses the local MAC address to deliver it directly to computer B. By enforcing a strict separation between local switching and global routing, engineers create vital security boundaries and allow networks to scale endlessly without bogging down. The internet operates as a highly disciplined, hyper-fast physical relay race. Millions of times a second, switches and routers execute these handoffs in perfect harmony to ensure the message always reaches its destination.